Okay, welcome back. So now that I've got basically the points in which I'm going to use to generate my numbers from in the right data structure, I'm going to start creating some of the members. And the first one we're going to look at is the rafter member. And just going back to the diagram here, I've got a curved rafter member. So I want this to be, I guess, curved, and I want to also be able to, I guess, define the radius of this curve if I want. And I've also got, from the original image, if I go back to that, I've got some extensions here which I'll probably want to show as well, but they're not going to be, I guess, a part of the overall structure. But I might want to define those separately. So in order to do this, I'm going to start off by generating a line between the two between those two set out points that we've defined separately, and I can again see where this line component, so it's a curve, primitive and line, and I'll just turn this on, and you'll see here that this has drawn a line between these 2 points. Now this is a straight line, and the reason this is done here is because of basically the way that it's tree matching. So it's basically drawing, because there's only one point in each branch for the start and the end, I'll get a resultant tree of one line for each branch. If I was to flatten these, I'm going to get basically 11 lines in each branch. Now that's not what I want. So you just to be careful with those types of things. If you are getting results where you're getting large and large amounts of lines, it's probably more often than not something to do with the way that your tree structure is set up. Then what I want to do is basically get I'm using a horizontal frame component, which is basically gives me a plane at a parameter, and this plane is setting up basically a horizontal plane on that curve halfway between the curve, and you can see that there. So its unit Z is upwards, and then from there I'm doing something similar. What we did before was we deconstruct that plane, and I just want to move that center point a distance of 500 up from that center point, and that's going to allow me to define my rafter curve. So I've used this amplitude component here, which gives me a vector with an amplitude. Obviously, I can set the amplitude on that. So I can set this at whatever value, or a varying value here, to increase the radius of that curve. Okay, so I've got that point, and now what I want to do is basically interpolate or generate a curve between these 3 points. And in order to do that, I'm using the interpolate component, and what that component does is basically takes any number of vertices, and in this case it's only going to be 3, but basically these vertices need to be set in order, so start, middle and end, and I'm using a merge component here to combine these 3 points. So I want my curve to start at the backstay, so I can put that branch into D1. I've generated my middle points, so I can put that into D2, and I've also got my front curve, so I can put that into D3. And this is what I was talking about before with the merge component. in this instance, it will merge at the list level. So the item in tree branch 0 will be added to the item in tree branch 0 of D2, and similarly D3. So I'll have 3 items there. And if I go and look at my point list again here, set that to 500, I'll see that I've got 0, 1, 2, and 0, 1, 2. And once I drag those results into the interpolate component, I'll see that I've got a line that goes from 0, 1, 1, and 2. So this is basically setting up my rafter at each section. And I'll just turn these off because I don't care about these components here now. Now that I've got my my rafter member. And okay, so in order to now look at my or just get my little extension components, I'm going to I can wire this curve into an extend curve component. I'll get my preview there. And then I can specify a start extension and an end extension to get those little extension parts on that curve. And I'll just turn off the preview of this one here. So the extend curve is not the curve I'm going to be using to, I guess, generate all the purlins and other members. So I'm just going to drag this one down out of the road for the moment, because I will be coming back to it. But the primary curve I'm going to wanting to be, I guess, developing my purlin spacing and that off is the one that comes out of the interpolate curve. So I'll just turn that back on. And now I'm going to want to generate my purlin members, and typically I will want these to be spaced evenly to get, I guess, the most efficient, the most efficiency out of purlin sections, and also reduce the, I guess, or increase the rationalization of these types of members. So I just want to use, I guess, an evenly spaced division of these. So in order to do that, I can divide that curve, or the curves that we've just generated, into a number of points. Now, I might want to, maybe I want to have, I guess, a division length in mind, but it might not necessarily have to be that exact value. And that's what I've done in this case. I've got I get a rough spacing I want in mind, because I want every purlin to be have an equal spacing, even at the start and the end. So what I've done is basically I've got the length of this curve using a curve length component again, and I'm just going to divide that by my anticipated purlin spacing. So in this case, you know, I want to aim for a purlin spacing of 1.4 meters. And I'm using an integer division here. So basically it will give me, it'll spit out the integer. An integer is a whole number closest, which will give me the closest, I guess, length or count number that I want to divide this, this curve by. So now basically what I'm wanting to do is I'm going to use these points for a number of different things. As you can see, there's a lot of wires coming out of this one. So if I just look, hover over this point, you'll now see that I've got 11 branches, 0 to 10, and each of those has 11 points in it. So if I look at my point list, and I use a point list component a lot to understand how my tree structure is working, and you can see I've got 0, 1, 2, 3, 4, all the way up to 10 for each branch. Now this is where it's going to get a little bit more complicated, and for a number of different reasons. So the first thing what I will do is define my purlin lines. Now in order to do that, what I need to do is get the points which are coming out and perform an operation which is called flip matrix. Now basically what the flip matrix does is allowing us, instead of, if I just get that point list back, instead of ordering the points from 0 to 10 along the rafter, I can flip my matrix, and then what it allows me to do is order my points from 0 to however many of these are, 10 as well, because that's how many divisions I've got, around the rafter. So basically it's just flipping that list or tree structure. And that means that now I can generate a polyline between those points. So if I turn this polyline component on, the polyline component basically takes a list of vertices which I want to generate these from, and because basically in structural analysis I want to be dealing with line segments, not I guess radially curved or curved arc lines, I can generate those purlin lines from the polyline component. Okay, so I'm going to leave that one for now, and we'll look at how we generate these strut elements. So the thing with the strut elements is, now that we've got our purlin points, we want to kind of make sure, probably for a number of reasons, that these strut elements come in at a point at which a purlin already lands. So basically what we want to do is we want to find the closest point on this curve where a purlin lands, and then make sure that that strut will hit that, will connect to that point. So the way that we're going to do this is, I want to make it quite flexible in where I can, I guess, position these front and back cantilevers, and I don't want to really have to select which item in this point list to select. I want that to do it. I want to do it automatically. So I'm going to set up a little bit of logic here, which I'll just quickly run through, and which will enable this. So I'll just turn off this points list so it's a little bit clearer. So the first thing I've done is I've got my, the base curves for the rafter, and there's a component which is quite good for looking quickly at where a point lies on a curve. A curve between 0 and 1, so in terms of a parameter. Now, so this is the point on curve component again, Control Alt. That's in the curve under analysis, and what this does is it allows you to. I'll just turn these two components, the preview of these two components on. And what this does is allows you to wire in a curve, and you can move this slider around and basically output a point at that specific parameter. So what I've done is I've basically set up two of these, one for the front cantilever point, as you can see here, and one for the back one, which you can see moving there. Now, I don't want my strut to go specifically to this to the point here, but I want it to link up to the closest point, which I've defined as a purlin point based on my purlin spacing. And in order to do that, I've got a little bit of logic here. And so what I'm doing here is I'm taking this point which is being created or coming out of the point on curve component, and you'll see I've got 1 point for each rafter. And then I want to calculate the distance from that point to every other point along this rafter, which I've generated from my divide curve component. So in here I've got 11 points coming in. So the output of this will basically be the distance from point A, a list of different distances from point A to every point in point B. So if I just look at this with a panel, I'll see all these distances. Now, what I can do now is use a component which is a sort list component, and what that will do is it will sort the numbers or the distance numbers in order of value. So if I wire this in here, you'll see I get a sorted list, and that's the same for each list in the branch. And then what this sort list allows me to do is sort a separate list of the same length in parallel with the sorting of the keys. So I've inputted my points list into this values list, which means it's going to resort my points in parallel with these keys. So if I now look at this points list, I'll see that my this output of the values A, I'll see that my 0 is the closest point, my 1 is now the second closest, 2, 3, 4, and so on. So what I want to do is get the closest distance, or get the item, get that closest item, and then what I can do is I've got that point, and then what I can do is use that to generate my struts. Okay, so I've done, and I can generate my struts from my from the endpoint of my plinth line. So I've just got the top point there, and again it's the same data structure, 1 point, and then the endpoint which I've selected from this list, and I can draw my strut. So this allows me to, I guess, move this, but the strut will always connect to a purlin location, which is quite helpful. Okay, so this is the exact replica of this for the front cantilever, and you can see I've drawn those two struts in line. Okay, so the last, I guess, major connecting member is the backstay element, and that's simply going to be the two, a connection of the two lines that we've already generated points for back here with the curve plane intersection. So I'll simply just create another line component and drag those in. So there's my backstay. Okay. The last part, which I'm going to show you, is generating the roof bracing and some of the bracing for the around this back portion of the structure. And typically, potentially with these types of roofs, you might have some purlins which are a part of the bracing system, and some purlins that are not part of the bracing system, and you also might want to define the bracing system based on the location of these struts to ensure that, I guess, the bracing nodes in it at these points. This is a little bit of a tricky way of setting this up, but it works reasonably well for here. And what I'm going to do is come up with a way to dispatch the purlin polylines into, I guess, a line where we've got a normal purlin and purlins which are a part of the bracing system. And that's going to allow us to generate the bracing in our roof. So I've got a whole bunch of item index components here, and what these components do, I actually don't have a preview, but what they'll do is you can basically test an item, and that will an item that's available in a list, and then it will give you the index of that item. So I'm simply dragging into the list parameter, I'm dragging the points along the rafters, and I basically want to generate a list of integers or indexes where the I guess the axial purlins will be located. So this first one, I know that I'm going to want an axial purlin at the first item. So this is simply just generating this. If I click on the panel here, at the first strut location. So this one is at the second strut location. This one here is at the final strut location, and I can click on these elements. So this is the first point, this is the end point, and what I'm generating is just a list of integers. Now, what I want to do here is, for instance, if I just, if I just click on these points, I might want to have, I guess, bracing. I know my bracing will be fine, I guess, if I want to have some cross bracing through here, but this dimension might be too large. So what I want to do is, I know I'm going to want another strong or axial purlin in between these two strut lines. What I do is I've basically calculated an input average to also generate the an additional index in which I want to apply a strong purlin line. So you can see now I've got basically the indexes I want. I want normal purlins, and well, these are the ones that I'll want a strong purlin at. Again, I can sort that list, and then, because I know that this structure is, or each of these tree branches is exactly the same because it's a very uniform structure, I can start just to work with flattened trees in this instance, because this bracing is going to be very uniform. So here I'm literally just taking the first path of this branch, which will just give me my single list of items because they're all the same. So I can go back to my purlin. I can go back to my purlins now, or my polylines, and I can flatten that list as well to work with single lists. And here I'm just going to basically dispatch this. So to get the items which are to be strong purlin lines, I'll wire these indexes into this list. So these are going to be my strong purlin lines, or my axial purlins. And to get my normal purlin lines or my standard purlins, I'm going to use a cull index component, and that will basically cull those items out of the list. So now I've got basically two separate lists that I can work with. So there's nothing else I need to do for my normal purlin components, so I can just have those as an output ready for generating my structural analysis model. And what I need to do with my strong purlin lines is start to generate my bracing. So I'm going to start by just using an explode component, and what an explode component will do is explode a polyline and produce its segments and the points that make up that polyline. It's the opposite of creating a polyline, basically. Now, in order to generate these bracing can sometimes be a bit more complicated, but what we're doing is first I'm going to generate the bracing in the first and the end bays, and then I'll generate a row of bracing around the perimeter. So I can again use this tree branch component, and this is going to give me my first is going to give me my first branch of points. So you can see those along the back. I'll just go back to perspective view. And then this one is going to give me my my first branch. And what I want to do is, because I'm going to define the front and end bays separately, I'm going to use a cull index to basically just remove the first and last index in that list. So if I just turn that on, you can see now that my list, there's no point at this end here, and same thing with here. And then I can just use we do have some components which do help with these connecting point sets and stuff in the Boolean plugin. There are a couple of improvements we're going to make to these components, but basically this connect points allows you to connect one set of points with another set of points in a pattern format. In this case, we want to do a zigzag, and I've created two of these to give us our bracing in our roof, or at the back there. And then I've done a similar thing here to generate our front and end bays. Again, I'm using the flip matrix because now I want to generate my bracing in the rafter direction. I'll flip the matrix. I'll turn that off. And I'm going to use basically I'll turn these components on. Preview. When you're dealing with lengths of trees and counts of trees, you can use the tree statistics component, which basically will count how many paths are in that tree. So I can count how many lists are in the branch, and I can also count, pardon me, how many items are in that list. So because I want to get the basically the first and last items to generate these points, I can do it using here. So I've basically got my my last branch and my branch one, the branch inward from the last branch. I've got my first branch and the second branch here as well. And using these components, I'm doing a similar thing and connecting all those points, connecting those points up. So now I've got my my bracing, and you'll see that my bracing goes over the normal purlin lines. If I just click on this, and it only connects with the purlins which I've got in my strong purlins or my axial purlins. So you can automatically see where your I guess the lateral system of your structure is, how it is working. And again, if I change my purlin spacing, I don't know, to 1200, this automatically gets updated, or whatever. Okay, so after generating the bracing, I've just merged all these elements into one. The last part, or the last bracing, is just generating the bracing for the around the back of the back of the pavilion, and I've just dragged up my my backstay lines, because it's going to go to the end of these backstays, and I'm going to use basically the endpoints of these. So I can get, again, I'll take the second and the second last, or the last and the second last, and you can use wrap methodology to do this, -1, -2, and the first and second items, and then basically generate some simple lines from those two things to generate your bracing. And here, this little symbol, basically what it does is reverses the list. So in order to get my crisscrosses happening, I've just reversed the start points, or the list of start points. So if I click here, if I don't reverse that list, I'll have 0, 1, I'll just copy this, and 0, 1, but as soon as I reverse that list, I'll have 0, 1, so my 0, so I'll get that crisscross methodology when I'm joining those two lists together. Okay, so now that I've basically finished the generation of the structure, I can merge all the components I want to, I guess, have as the same section size or same member methodology type. So I've got my vertical bracing in one list, I've got my roof bracing in one list, I have my axial purlins in as one list, and I'll turn the preview on. I've got my front struts, my back struts, my rafter polylines, my backstays, and my concrete plinth. And this is all parametric, so it's good to go back and start to play around with this. You can enhance your bay width. You might want to reduce or increase the number of bays. You might obviously change your input curve slightly to sort of understand how you can move this structure around a little bit. I hope you've enjoyed these videos. The next videos are going to go in depth into space gas, and we're going to start building a structural analysis model using the geometry that we've generated.